Living part of soft matter. I'm pleased to introduce the next speaker, Andrea Liu. She's many things. You could read her biography, but I want to say two things. One is she's director of the Center for Soft and Living Matter, which is a relatively recent center at Penn under her direction, bringing together all the topics we're talking about and then some. And secondly, we overlapped at Cornell. I didn't realize that when I looked at your bio. I was in material science and you were in physics.
Okay.
So that's the second thing. So with that, we're going to let Andrea talk about AE for autonomous learning.
Okay. Thank you. I feel a little bad because I actually chopped out the living matter parts. So I'm just going to be talking about autonomous learning today. But this was actually motivated by a living matter system, and so I'll talk about that. So and here it is. So the original motivation, well, the original motivation for a lot of this work was Allisterian proteins. Okay, it turns out that proteins, you can think of it, folded proteins. A lot of people think of them as mechanical networks, and it turns out that flow networks and mechanical networks are very similar mathematically. So we got interested in this flow network problem, largely, really at the inspiration provided by my colleague Eleni Kadafori, who studies flow networks. So she pointed out that the brain vasculature does something very similar to Allisterian proteins, actually. So it turns out that the brain uses a lot of the oxygen that we take in, okay? And it uses it to support brain function. And depending on what part of your brain you're using, okay, that part of the brain needs more oxygen. And the brain vasculature is responsible for supplying that extra oxygen that my speech cortex is needing right now. So what's happening is that blood is coming into my brain through the large pressure, through the arteries. So there's a lot of flow there, big pressure drop across the arteries. And the brain vasculature is adjusting itself by contracting some blood vessels and dilating others. So this can be thought of as a network with about 1 million edges, okay? And these edges are adjusting their conductances in real time to deliver a big output pressure drop or a lot of flow, extra oxygen to my speech cortex, okay? And so that's really quite a remarkable thing that the brain vasculature is doing. So that got us thinking about how to do that, okay? Now, I want to just point out that this is low Reynolds number flow in these networks, and so this problem is identical to a problem of electrical resistor networks, okay? So if you solve one problem, you solve the other. It's just that for a flow network, we talk about pressure. The equivalent in the electrical network is voltage, current is current, of course, and conductance is conductance. So everything just translates perfectly over. They're exactly the same problem. All right, so the question was, now how would we design a flow network, okay, to deliver a desired pressure drop at a desired location, the speech cortex, right? How would you adjust the conductances of the network to get that? And that's the same then as saying, how would I adjust the conductances in an electrical network to get a large voltage drop at a certain place? Okay, so usually the way people solve it, right, is what we're used to solving is the forward problem. In other words, what is the voltage at the output, okay, given some input voltage, right? Then you crank through the problem, you solve the problem, and you get the answer. That's something we know very well what to do. But here we want to solve the inverse problem, right? Which is we want to know what network will give me the pressure drop or voltage drop at the target that I want, okay, in response to the input pressure drop or voltage drop, okay? So, so the way people usually solve it, right, is by exhaustive solution of the forward problem and then interpolation, okay? But here we have a network of about 1 million edges. Each of them can have a different conductance. That's a very, very high dimensional space to be working with in. And interpolation, exhaustive solution of the forward problem in interpolation is never going to get you there. All right, so what we ended up doing was what I call machine learning light, okay? So, so the idea from machine learning that we know, right, is that the way you solve the inverse problem, so that you give it pictures of dogs and cats and you get the right answer, dog or cat, right? We want to know, that's the same question. We want to know what's the network that's going to give us the right answer, okay? So the way you do it is you start with some network, you get whatever answer, you get some outputs here, you compare it to the ones that you want. You don't know which is bigger, so you square it and you add these all up. Okay, that's what we call the learning cost function, and then you minimize this with respect to learning degrees of freedom, for example, the node weights. Okay, and then you do gradient descent on this learning cost function, adjusting these learning degrees of freedom, okay, until you reach the global minimum of 0. Okay, and then the output that comes out is the one that you want. Okay, so that's how you train these systems. So let's do the same thing, okay? Let's take a flow network. So here's a flow network. This is with periodic boundary conditions, okay? And I have a pressure drop, let's say, of 1 across these 2 nodes, okay? And let's say I want a pressure drop across these 2 nodes of 0.2, okay? Well, I start out with a pressure drop of 0.003. That's not what I want, okay? So I compare it to what I want, which is 0.2. I don't know which is bigger. In this case, it's smaller. Okay, I square it, okay? And then I'm going to minimize this learning cost function with respect to learning degrees of freedom, which in this case are the edge conductances. All right? That's great, right? That's just like the neural network, solving a neural network, training a neural network. Except that this is a physical system, okay? And because it's a physical system, there are physical constraints that must be obeyed as well. In particular, you need to minimize the power so that you get Kirchhoff's law satisfied at each node, no net current at every node. You have to have that, okay? And so you have to adjust the physical degrees of freedom, which are either the node pressures or the edge currents, okay, to satisfy that at every node, which is consistent with minimizing the dissipated power. So what this calculation comes out to be is you first do the forward calculation, right? You say, okay, I apply a pressure drop of 1 here, what comes out here, okay? And when you do that, you have to minimize the physical cost function, okay? For your given set of conductors, you have to minimize it, satisfy Kirchhoff's law, figure out what comes out here. Then you compare it to what you want, okay? You take a step in gradient descent by adjusting your conductances, okay? But once you've adjusted your conductances, you're no longer satisfying Kirchhoff's law. So you have to go back and adjust, okay? Again, to minimize the power so that the net current at every node is 0, okay? And then you take another step. So that's the equivalent of forwards, backwards in this system, okay? And you just keep doing this until you reach 0, the global minimum of 0, and then you've achieved your desired pressure drop. Okay, and that works, and this is that process in motion. Okay, the pressure at the target, we're reading it out. The conductances here are being tuned. You can see the lines, or the thickness of the lines are the conductances. The blue dashed ones are ones that effectively reach the minimum conductance and are removed. And at the end, you saw it reach the desired value of 0.2. Okay, so that's great, okay? But it's not autonomous learning, okay? Why is it autonomous learning? Well, this was all done on the computer, and there are 2 parts of it. The 2 key parts of it both require, this autonomous learning. So first of all, to do the forward calculation, to minimize that physical cost function with respect to the physical degrees of freedom, like the node pressures, required computation, okay? Then the second part, using gradient descent, to minimize the learning cost function with respect to learning degrees of freedom, that also requires computation, okay? So this network is not learning on its own how to do this, okay? And these are global processes, and they require knowing every little detail about the network, right? You have to know everything about the network. You have to know all the edge conductances. You have to know all the connectivities of the nodes in order to evaluate the learning cost function, in order to minimize the physical cost function. You have to use a processor to calculate the gradient descent, and then you have to go in there and individually modify each edge in the right direction, okay? So that's not scalable. If I wanted to make a big system to do this, I wouldn't be able to do that. So that's not good enough. And actually, this problem of this being a global problem is a hindrance for artificial neural networks, which now are extremely large. They chew up enormous amounts of power to run, and it takes us a long time to train them, okay? Because they're global. So the question was, can materials learn function autonomously, okay, without a processor? And here, right, we look at the brain. The brain is not connected up to a computer, right? The brain is learning everything on its own. It doesn't need a processor. Learning is distributed among all the neurons, and the neurons are updating their synapses. They're doing all this under local rules. There's nothing global about this, okay? And yet the brain is much more powerful at certain things, and at the things that, of course, humans think are important, than an artificial neural network. It uses much less power than, a fraction of what we eat to run, and it can be much faster at a lot of tasks, right? So can we do that? Can we make more materials that learn more like the brain? So here's the idea that's really due to my fantastic postdoc, Naki Stern. So the idea is to take from contrastive learning. So remember, our learning cost function was, let me first define what I mean by the free boundary condition. The free boundary condition is that I just apply the pressure drop I want at the source, okay? So I apply a pressure drop of 1 at the source, and then I leave the target free to be what it wants, okay? And generally, it's not going to be the value that I want, okay? So I'm going to compare that to the clamp condition where I apply the source pressure drop of 1, okay? And here now I apply the desired target pressure drop, okay? Which is not the same as what it would naturally give, okay? And so our original cost function was to take this free response, okay, and compare it to the desired response, and we don't know which is bigger, so we square it, right? So we're going to, instead of doing that, we're going to say, well, the clamped is where I apply the desired target response. So what I want is for the free to equal the clamped, okay? So instead of saying what I want is the free result to be equal to clamped, what I'm going to say is I'm going to look at the power of the clamped minus the power of the free. Now, the great thing about this is that the clamped, we're taking the system away from where it would naturally be at the target. Therefore, that actually costs more power. That costs power, okay? So physics tells us that this clamped power has to be greater than or equal to the free power. This, we do not have to square it in order to know that it's positive, that minimizing it will take us to the right answer, okay? That gives us a huge advantage, which is that now we do gradient descent on the conductances. So let's adjust the conductance of edge J according to going downhill and the gradient of that. When we put this in, we know that power is v squared across that edge, right, times the conductance of that edge. So in the clamped and the free, and you take the derivative, you just get this. And you see that the adjustment of the conductance of edge J just depends on the voltage drop across that edge. That's all you need to know. You don't need to know what's happening elsewhere in the circuit, okay? Now, of course, the voltage drop across this edge depends on what's happening elsewhere across the circuit because we're satisfying Kirchhoff's law at every node, right? Everything's coupled, but we don't this edge doesn't have to know all that. It just has to know what's on that edge. Okay? All right, so that's a purely local rule. So that's great, okay? So instead of doing this gradient descent on the learning cost function, we've replaced that with this coupled learning rule, but we still have this problem that minimizing the physical cost function, satisfying no net current on every node, is still, computational and is requiring a processor and actually pretty time consuming. Okay, so this is where you notice that, what if you did it in the lab? If you actually did this, right, in the lab, not on the computer, then physics would do this for you. You wouldn't have to lift a finger. Physics automatically will reach a power minimum and satisfy Kirchhoff's law on every node, okay? So that forward calculation becomes free. You don't have to worry about it. So how do you implement it in this lab? And this is where Sam Dilvu, who's sitting back there, and Doug Durian, who's sitting here, that's where they come in, because they built this thing in the lab. All right, so you can buy, the first generation is based on the idea of digital variable resistors, which have a bunch of resistances and you can just click them up or down, okay? But the problem is, if you look back at this coupled learning rule, okay, you need to compare the voltage under the clamped condition with the voltage under the free condition. Those are two different boundary conditions, and you can't apply two different boundary conditions at the same time, okay? So how do you get around that? This is very clever. It was to say, and on the computer, right? You calculate one, you stick it in memory, then you calculate the other, and you pull it out and compare them. We don't want to use external memory. We don't want to use a processor, okay? So how do you do it? Build two networks, okay? Two networks that sit right on top of each other, two identical twins, okay? And now the idea is one of the twins is running the free boundary condition, the other one is running the clamped boundary condition, okay? Each edge then is actually two edges, okay, that are then linked by circuitry, which does this. It compares the voltage in the free and the clamp state, the magnitude, and clicks the resistance up a notch, depending on which is bigger, or down a notch, depending on which is bigger. Okay? So this is actually not even the exact coupled learning rule. It's an approximation to it. Okay? So this is the first generation. Okay? 9 nodes and 16 edges. Okay? All built by hand. And the crazy thing is that it actually works. Okay, so this is an example of it classifying this iris data set. So the iris data set has 3 different species of irises, okay, and you give her 4 measurements, these 4 measurements, okay, and then the task is to classify these irises into their 3 correct species based on these inputs, okay. There are 150 flowers altogether, 50 of each. Okay, so the idea is now you feed in these 4 measurements as voltages through 4 nodes, and one of these is ground. Okay, one of them sets ground, and then there are 3 species, so you report them out through 3 different through these 3 nodes here. So depending on which is biggest, that tells you which species you've got. Okay, and what you see is that you train it on, I think, 10 examples from each set. And then look at the test error, and it's about 97%. It's amazing. That's what you get with the linear classifier in the computer. Okay, so but the great thing about it is that if you want to teach it something else, you just change the boundary conditions. You just change what you mean by the clamped case, and okay, or the free, and the free case. You don't have to change the learning rules. So you don't change the circuitry. That all remains the same. You just apply different voltage inputs and outputs. And so it can learn one thing after another. Okay? So first you teach it, classify the iris data set. That's this. Okay, this is the mean squared error. And then you say, no, what I want is, okay, I'm going to set this node to ground, okay? I want to put in a certain voltage here, and I want a different voltage coming out at this output here. Learns that, okay? I have one source and two targets of different voltages. It can learn that. Okay, two sources, three targets of specified voltages. It learns that. Okay, one source and four targets. Okay, and then you say, no, learn linear regression. Learn how to solve two equations and two unknowns. So it solves that. Okay, learn a different set of two equations and two unknowns. It can learn that. Okay, interestingly, now you take it back to this. Do this again. And I forgot it. The error went up again. So you have to train it again. Okay, and in fact, you find a different solution than you found the first time. Okay, so this thing can learn adaptively, one thing after another, indefinitely. All right, so it is sort of poised halfway then between artificial neural networks and the brain. Okay, so one of the amazing things about the brain, right, is it can sustain a lot of damage and still people can still function. For example, there are people with severe epilepsy who have half of their brains removed, and there was a recent article, I forgot where it was, saying that they can do facial recognition just as well, okay, as people with whole brains. Okay, so brains can sustain enormous amounts of damage and still work. Is that true here? And yes, it turns out that you can rip out 5 edges out of 16 and it can still learn the task. Okay, it just relearns it, no problem. Okay, so it's very robust, and that's because learning is distributed among these edges. Each edge is learning on its own. Okay, so if there's damage, it just finds another solution. It finds a way around it. That's the first generation. Here's the second generation. Due to Mark Miskin, who's in ESE. And so the second generation is now an analog version. It implements the exact coupled learning rule. But the resistance it's not totally linear, okay? It's a little bit nonlinear. And it's actually nonlinear enough, it turns out, that it can learn how to do nonlinear classification and XOR. So these are things that the linear circuit with just a simple resistance cannot learn. Okay. The great thing about being based, there's a picture of Sam with the second generation prototype. Okay. So the great thing about, just to show you, here's a nonlinear classification task where you want to find out what's inside the circle. Okay, so class 1, or outside. Okay. So you want correct classification is to figure out what's inside and what's outside the circle. You start training it, and eventually it gets everything right, what's inside and what's outside the circle. And this is just the process, okay, of it learning. What was I? Oh, yes. Okay, sustainable learning. Okay, so as I said, artificial neural networks take immense amounts of power. Okay, so our circuits are much less power hungry, and in fact, scaling arguments, very preliminary scaling arguments by Marcelo Gutzman, who's sitting back there, show that the scaling of the power required to train a network actually goes down as the system gets bigger. And why is that? Well, you've got the power roughly, think of v squared over r. As you make the system bigger, they're more in parallel, they're also more in series, and so the net result is that the resistance actually goes up, the effective resistance goes up, and the power consumed by the circuit actually goes down. Okay, so that's good, but it can be better than that. So, for example, if you start out v squared over r, if you start out with really high resistances, right, then you'll be using less power. So you can initialize the system to have high resistances, and then you reach a lower power solution. But you can even do better than that. Okay, so all of these things help reduce the power that these things are using. And why? And so here's the real thing. The contrastive function here, the difference between the clamped and the free, is built in through the power. The power just automatically appears in the way we formulate the problem. Okay? And that makes it really easy. Oh, this is just totally, sorry, in the wrong place. Let me come back to this. This is really important, but let me come back to this. I just totally screwed up where I was placing my slide. Sorry. So this contrastive function is based on power. And because it's based on power, it's really easy to say, well, let's not only optimize to minimize this thing, okay, my cost, okay, the error, okay, but also optimize for power. So in addition to this, I can add a piece which is just proportional to the power in the free state. So now, if I minimize this thing, I not only want to lower the error, but I want to lower the power too. Okay? But there's a trade-off. Okay? The most extreme example is that if I let this out, so if I make lambdas very, very large, okay, then I just want to minimize the power. Okay? And the power is going to be really happy. But if I leave that out, leave this term out, and just minimize this, then in terms of error, I'm happiest with error, right? So and there's a balance. And so as you increase this parameter lambda, what happens is that the power can go down, okay, but the error goes up. And you see that you see that in the experiments. These are the experiments on the circuits showing that as the error goes, as this is error versus power, as the error goes down, the power goes up. Okay, so that's that trade-off. Okay, but these networks have some level of error anyway. We're not trying for zero error. These are not perfect networks. These are in the lab. Okay, so there's some error floor. And so there's no point doing better than the error floor. Okay, and so what Naki has done is to say, okay, let me come up with a way of adjusting lambda in time to get to a lower error power solution. Okay, and he's come up with a way that works pretty well. Okay, so this is the desired error. This is the error you actually have, and you adjust your value of lambda according to that, and you can gain, like 30% power or something like that. Okay, 30% in power. Not nothing, okay? But, oh, okay, Siri can't help us. Okay, so we can get lower power solutions by varying lambda. Okay, so now I'm going to descend below what my friend Sid Nagel calls the bullshit line. Okay, so everything that I said so far, it's based on something, you should believe it. Okay, but now I'm descending below the bullshit line and I'm starting to speculate. Okay, but the idea is, wouldn't it be cool if we used automatic experimentation to vary lambda? In other words, we could use information about the current electrical state and error, okay, feed those in as inputs, and the output is the new lambda that we want to change to in the next state, okay? And we adjust lambda then on the fly for each case, for each time we want to train, to lower the power, okay? I think that's actually not unrealistic to do. And so that's a way in which we can use this idea with autonomous experimentation to lead to more sustainable autonomous learning. Okay. Okay, before I do that, I want to come back to this thing that I forgot to say, which is, so the second generation I'm incredibly excited about because, okay, they've already speeded it up from each training, the training step, the time of a training step to do this step and gradient descent on the learning degrees of freedom on the conductances, and was about a second in the first generation. Now it's 10 to the minus 4 seconds. So it's speeded up by 4 orders of magnitude, probably speed it up a little more than that, okay? To the point where the second generation, even on a breadboard, is actually a little faster than doing the same thing on the computer, okay? So, and the scaling is so great of training time with system size. Again, Marcelo's preliminary calculations indicate that the training time increases with the 0.2 power of the system size, which is incredibly small. Okay, so great scaling. So the bigger this gets, the better, the bigger the advantage over conventional artificial neural networks. So the next step is to put this on printed circuit boards. We're looking at we'd like to be able to microfabricate these networks onto a chip. Okay, so millions of nodes on a little chip, and that then should give us a massive scaling advantage when you get to that size. Okay, and all at low power. And the point is that, you know, a lot of neuromorphic things, they really need perfect manufacturing in order to get everything to work. Okay, because learning is distributed in this system. Okay, each neuron, and I showed you it's incredibly robust to damage. That means that you can make all kinds of manufacturing errors and it should still work. In fact, a problem that Sam had in testing his networks is that they just kept working. And it was very hard to tell whether a given edge was behaving the way it should because the whole network was working. Okay, that's the kind of problem you'd love to have. Okay, so we're very excited about this, all right? But this is only part of it. So now I had to skip over this part. Okay, maybe we can use, now this whole, just this one slide is below the bullshit line, right? Is maybe we can use autonomous learning, experimentation, to explore the space of learning degrees of freedom to obtain better solutions, more generalizable solutions, okay? So, so the first thing to do is to learn about how the system manages to learn, okay? In order to use that to guide us to try to find ways to learn better, okay? So, and that's a hard problem, actually. That's a very fascinating problem, one that's interesting to neuroscientists as well as statistical physicists, right? Because learning is a collective property that emerges from a bunch of identical components evolving based on local rules. Okay, so then somehow they're coupled together by being at the minimum of the power dissipation to have learning emerge at the collective scale. It's a many-body phenomenon. Okay, but it's the kind of many-body phenomenon that's really hard for statistical physics to handle. Because what we're good at is either systems that have complete order or complete disorder. So obviously, if all the conductances were the same, it wouldn't be learning anything. Okay? If all the conductances were completely random, it also can't do anything, right? The conductances are different, but they've been correlated, that disorder has been correlated in order to give the right answer, okay? In order to have learned. So, and that's a really hard problem to solve, okay? So one thing we know from statistical physics, though, is if we want to solve something, we need ensembles. We need ensembles of systems that have all learned the same thing, okay? But that are different. But now we have them, right? The second generation reports out every detail of the electrical state as this thing is learning. So we have all that information, and we can set it up with different initial conditions, same task, and we can learn the same thing over and over and over again and get different answers. Okay, and we can look at that ensemble of answers and say, okay, what did it learn? How did it learn it? Okay, so so that's the question. How does this how did either getting a desired target voltage or classification, how do these things emerge? Okay. So, so we started looking at this in the context of flow networks. In the case of, for example, the brain vasculature, where I have some pressure drop of 1 and I want some target pressure drop there, okay? And we started wondering, how does the system manage to do that? Okay, and when you don't know what to do, you look at extreme limits. And in this case, the extreme limit was to say, I'm going to tune this target pressure drop to have it to be exactly the same as the source. That's the biggest it can be, okay, is 1. And if I tune this to be 1, what we find is the network always does the same thing, okay? It always breaks, this is with periodic boundary condition, it always breaks into 2 sectors of different pressures. So here's a sector where all the nodes have the same pressure of -0.5. Here they all have a pressure of +0.5, and the 2 source nodes and the 2 target nodes span the boundary between that sector. That's what has to happen in order for this to work, okay? If you look at it, so you get these very large pressure drops, okay, across these things, across these edges here. If you look at this, you say, that's interesting because that's a topological thing. And we know it's topological because we can count. We went from 1 sector to 2 sectors, 1 network to 2 networks, okay? That's counting. That means it's topological. The second thing that tells you it's topological, right, is that you can see it doesn't depend on the shape of this boundary. I could have routed the boundary this way, okay? But as long as the target and the source nodes span that boundary, I've got a pressure drop of 1. I've done it. Okay, so it doesn't depend on the geometry of this, it depends on the topology. Okay, so if it's topological, that suggests to use topological data analysis, so we looked at persistent homology. And I'm not going to go through it, but just to show you that persistent homology gives you sectors, okay, that now have not uniform, in the extreme case, they're completely uniform node pressures, but in this case, they're not quite uniform. There's some variation in the size of these pluses within a sector or the size of the minuses, okay? So they don't have all the same pressure, but they're close, okay? And it turns out, so this is a task where you have 1 source edge with a pressure drop of 1, and then you have 6 or 7 different target edges that you're tuning, okay? And to be at least 0.25 pressure drop across the target nodes, okay? And so if you look at the average pressure within this sector and the average pressure within this sector, and then compare that to the pressure drop across these 2 these 2 nodes, target nodes, okay, what you find is they're very, very close. So if you make a plot of the mean sector pressures, the difference of mean sector pressures versus what was actually tuned in, it's nearly this dashed line, which is they're equal, okay? So just looking at the sectors, we can pull out the pressure drop, okay, that was tuned in. We can pull out what it learned, okay? And it gives a very nice way of thinking about things. And just to show you, these are sectors. This is done by Felipe, who you heard from this morning, who's sitting back there. This is a movie of the sectors. It's that movie. Okay, so these are the sectors that the system eventually forms. This is one is the source, one is ground. That's ground. That's the source, and there are 5 different target nodes, and you can see the system evolving as it's learning. Okay, and we can just watch it happen. Okay, so that's not the only way to think about this thing. There's another way we can think about this problem. So we've got 2 different landscapes in this problem. We can think about the learning cost function as a function of all the conductances on each edge, right? So that I have a conductance on edge 1, conductance on edge 2, conductance on edge 3. Each one is a different orthogonal direction. I have this very high dimensional space in which I can think of the learning cost function as the height in this very high dimensional space. At the same time, we have the physical cost function, which is the dissipated power as a function of the voltage on node 1, the voltage on node 2, et cetera. Okay, the physical degrees of freedom. So I've got 2 different landscapes that are coupled together in this problem, okay? And a useful thing to look at is this physical landscape, which is the power versus these should be voltages. Oh no, sorry, this is the landscape. this is the learning landscape, which is the dissipated power versus the conductances. But I could also look at the physical landscape, which is, this is, okay. Should be the dissipated power versus the voltages. Okay, and I can look at the derivatives. I can look at that landscape, and I can look at the eigenvalues and eigenvectors of the second derivative of this. I'm sitting at a minimum, so the first derivative is 0. So the next term is this second derivative, okay, and I've got the curvatures in different directions. So the eigenvalues and the eigenvectors give me the curvature. The eigenvalues give me the curvatures. The eigenvectors give me the directions. Okay, and you can think about how does learning change that physical landscape as the system is learning. And the cool thing is that it takes these eigenvalues, the curvatures, and it brings them down. It flattens it out. It flattens out this landscape so that the curvatures are lower. And in particular, one of the modes is quite low. I'm going to just skip this great stuff, which I'm so excited about, and just say that, this gives us another window on how the system is learning through those modes, okay? Those eigenvalues and eigenvectors, and, the flatter the system is, maybe the more generalizable the solutions are. If we're doing something like classification, these are all things that people are worrying about in artificial neural networks. We can think about the same things in these networks, how to get more generalizable solutions. And this is where I think automatic AE experimentation will be extremely helpful to explore that parameter space. All right, so let me just finish by showing you the pictures. A lot of them are in this room, so you can just talk to them. And thank you for your attention.
So we have time for questions for Andrea.
Thank you. Great talk. So I have a couple of questions. First, you talked about the power accuracy trade-off.
Yeah.
Right?
Yeah.
Is that the power involved in training the entire thing, or just at the inference stage?
That's the power at the end.
Okay. And so that's very great, because I'm thinking of the power as a measure of sustainability, right? So sustainability performance metric. How does the power speed up trade-off looks like? So when you use less power, does the computational performance go down of the network, or is not affected?
No. So for example, one easy way to change the power is to start with high resistances. It doesn't matter what resistance we start with, the training time is the same.
I see.
So there is actually no trade-off between time or accuracy and power.
I see. And then,
yeah.
Go ahead. Well, in terms of analogy with artificial neural networks, is there a dropout layer or anything, that you're turning off resistances when you train it?
No, but we can do that. That's a really cool thing, is that we could train it with dropout and then make it even more robust to error. Yeah. So yeah, we haven't even bothered to do that yet, but it would be really, really cool to do that. That's on our list. Yeah.
Thank you. That was really cool. With regards to the robustness that you just mentioned, is there a logic, say, in the first generation when you're just snipping connections, to what connections can be removed and everything stays the same?
Yes, in fact, I sort of skipped over that, but Sam found that he had to really work to find edges where snipping them made a difference. Most of the edges, if you snip them, you don't even have to retrain it. It's fine. It still knows it. Okay, so he had to work to find ones that if you snip it, it really makes a difference. And you can see that from the sector picture, that it's the edges that are at the boundaries of sectors that really matter. And if you snip other ones, not a big deal. Yeah.
With that in mind, just a quick follow-up. So in a really big system, say if you have a simple problem that you're looking to solve and another simple problem that you're looking to solve, if you had two far apart sectors, could you simultaneously solve two separate problems?
I think so, yeah. And we can, right? We've seen that on the computer. Yeah. So it's these networks are extremely small, so they forget as soon as you try to teach them a new task, they forgot the old ones. But if it's large enough, that doesn't have to be, and if it's nonlinear enough, it also doesn't have to be, we think.
Time for one more question.
Hi, I guess I'm influenced by the physics training I have, but so you're talking a lot about like training networks for circuitry and voltages and resistances, and I feel like naturally I'm like, okay, we use circuitry models to model like everything in physics, right? So like, can you build systems like this that model other phenomena, or can you use this phenomena to study other type of systems like spring mass systems or something like that?
That's a great question. Yes. So the first question that we've been thinking about is how can we use these networks to solve mechanical networks with like central force springs, speed spring networks, just as you were saying. And we think we can. It takes some thought, okay? But yeah, yes, that would be really, really cool if we can use these as sort of analog computers to study other physical systems.
Are there other systems aside from spring mass networks? I feel like there must be, right? But
yeah. What? Yeah, fluidic systems, of course, are just, so fluidic systems are just mapped onto this. So one idea that we have is just to take what we learned from electrical circuits, print them out into fluidic circuits that have that function. Okay, so that's an easy one. Yeah.
So follow-up question, short follow-up question. Could you also work in AC? Could you have phase lags and have reactance and impedance and more generally?
Yes, that's something we have. Yes. So if we're doing AC with dynamical inputs, and then we can have dynamical outputs, the coupled learning, it's a little bit different. What you want to minimize, it seems, is the difference between the work in the clamp state minus the work in the free state. Okay, but yes, we should be able to do that. So yes, that adds a lot of richness to what we can do.
Let's thank Andrea for a very stimulating presentation.